Hey everyone, welcome back and thank you for joining us again as we continue our discussion on the inference about two means. However, this time we're going to be discussing independent samples. Well, heading into our objective then, we need to be able to test hypotheses regarding the difference of two independent means. First, we're going to highlight the fact that we're working with independent samples here, so our approach is different than when we're testing hypotheses regarding match pairs data. This is a big deal, but we'll discuss how to assess that when we get to our examples. In the meantime, let's discuss our requirements. Remember, we're discussing two different populations now, so that means to test hypotheses regarding two population means, which we're going to call mu1 and mu2, with unknown population standard deviations, the following requirements must be met. First, the samples must be obtained using simple random sampling, but we know that's pretty normal, and that's usually taken care of. Next, the samples need to be independent, and like we said, we need to be able to recognize that within the problem. The data cannot have outliers for us. But here's the big one. The populations from which the samples are drawn are normally distributed, but if we don't know that the populations are normally distributed, then the sample sizes need to be large, and we've seen this before, but now notice it's for each sample. We need the first sample size to be greater than or equal to 30, and the second size need to also be greater than or equal to 30. And of course, for each sample, the sample size cannot be more than 5% of the population size, but usually that's taken care of as well. Well, if that's okay, let's head over to the steps in our hypothesis testing. Hopefully this is starting to feel a bit familiar, but again we have to be careful with the language here. Notice this time, as we state our null and alternative hypotheses, we're now comparing mu1 to mu2. The null hypothesis is that mu1 is equal to mu2, and we know to change the alternative hypothesis based on the type of test that we're conducting. If it's two-tailed, then that means we have mu1 not equal to mu2. If it's left-tailed, then that means we're saying mu1 is less than mu2 as our alternative hypothesis. And if it's right-tailed, our alternative hypothesis would be that mu1 is greater than mu2. But hopefully that part is feeling decently comfortable. But with independent sampling, notice that we're comparing mu1 to mu2 and make sure we're careful with that when we're asked to state the null and alternative hypotheses. Once we state our hypotheses, we need to select the level of significance, which we know is alpha, connected to the seriousness of making a type 1 error, but we know alpha is typically determined by the problem and given to us. That takes us to our next step, which would be to compute the test statistic, this time being t0. Notice the formula that we're working with isn't exactly the smallest, so make sure we're a bit careful when we show that math. We know x bar sub 1 and x bar sub 2 would be our sample means from each sample. Mu1 and mu2 refer to the population means, but we're going to talk a little bit of theory here. This is the formula to find t0. However, when we apply mu1 minus mu2, that's going to end up being 0. But we need to ask ourselves, why is that? Well, remember, we're working under the null hypothesis that mu1 is equal to mu2. Well, if mu1 is equal to mu2, then that means the difference between those two would be 0. And since our null hypothesis is always mu1 equal to mu2, we end up being able to wipe out this part of the formula when we do our math. If that's okay, step 4 has us using the TCDF function, which we've seen before. Remember that we have to be a bit careful based on the type of test that we're working with, two-tailed, left-tailed, or right-tailed. And then remember to use the TCDF function in order to find the p-value. We need to input the lower bound, upper bound, and then our degrees of freedom. But with this type of test, since we're working with two different samples, we need to use the smaller of either n sub 1 minus 1 or n sub 2 minus 1 degrees of freedom. That is, we use the smaller sample size, if they're not equal, in order to determine the degrees of freedom for our TCDF function. If that's okay, the next step would be to state the conclusion, and we know the results of our test are determined by the p-value, or if the p-value is less than alpha, we know to reject the null hypothesis. Well, that walks us through the different steps for our hypothesis test in terms of a free response question, so let's go ahead and jump into our example. Well, our first example opens up with a researcher who wanted to know whether state quarters, yes, again, had a weight that is more than traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters, weight each of them, and obtain the following data. We're asked to test the claim that state quarters have a mean weight that is more than traditional quarters, at the alpha being equal to an 0.5 level of significance. Well, first things first, we know we have two samples here as opposed to just one sample because we're comparing state quarters to traditional quarters. We're not comparing the weight of these quarters to some fixed value, which would be a one population test. So we then have to decide what we want to call sample 1 and sample 2. Well, we'll call the state quarters sample 1, since they gave us that first, and that would mean our traditional quarters would be our sample number 2. The next layer would be making sure we understand why this is independent sampling. Well, first we're allowed to use deductive logic. We're told that he randomly selected 18 state quarters and 16 traditional quarters. Well, if we have different sample sizes, then it must not be matched pairs data because they wouldn't match up. Now that doesn't tell us directly that we have independent sampling, but it is a nice piece of evidence. That is, if we had selected 16 state quarters and 16 traditional, we would still have independent sampling here. So it's not enough to just know the fact that if we have different sample sizes, it must be independent sampling, because we may end up with the same sample sizes. However, if we are presented a question like this that does have different sample sizes, it makes it a bit easier for us to recognize it must be independent sampling. Instead, to recognize independent sampling on a deeper level, we need to recognize that they are not comparing one quarter to another quarter. Instead, we are simply comparing one group to another group. Just to elaborate a little bit, jumping back to a previous example, working with match pairs data, this discussion is concerning hotels, and we're comparing the Hampton Inn to La Quinta. We're told to test the claim that the Hampton Inn hotels are priced differently than La Quinta hotels at the alpha being 0.5 level of significance, but notice our data is gathered by city here. That is, we are making a direct comparison of a Hampton Inn hotel to a La Quinta hotel only in the city of Dallas, and then a direct comparison between Hampton Inn and La Quinta in Tampa Bay, and so forth and so on down the list. That is, this is a match pairs design since the hotel prices come from the same 10 cities, and again we're comparing directly. We are not simply comparing Hampton Inn hotels to La Quinta. Now for the sake of conversation, if they didn't give us that extra bit of information that would be the cities from which each set of data is gathered, then we might have to treat this as independent sampling. But since we know it's a direct comparison based on the location, meaning those cities that these hotels come from, that's what makes it match pairs, which sends us down the different route in our hypothesis test. Heading back to our example then, we have our state versus traditional quarters, and we know that we're working with independent sampling, so we're ready to head into the details of the test. Well, first, we're going to throw the state quarter data into our L1 and our traditional quarter data into L2. And once we have that taken care of, we're going to go ahead and check for the requirements to make sure we can conduct the test, but we'll go a bit quickly through that if you want to trust me. We have independent samples. The sample sizes are small, so that means we have to verify the data come from populations that are approximately normally distributed. So that means we would construct a normal probability plot like we've done before, and a box plot, but instead of going through all that, like we asked, if you don't mind trusting me, we'll move on. We're all set with our normal probability plots, and we have no outliers, so that means let's go ahead and jump into the test. Heading into our hypothesis test then, first taking a look at the setup, we want to determine whether state quarters weigh more than traditional quarters. Remember, we call the state quarters our sample number 1 and traditional quarters sample number 2, and that's just making sure that we're careful with our organization here. Well, we know the null hypothesis would be that mu1 is equal to mu2, and since we're saying that state quarters weigh more than traditional quarters, that tells us we have a right-tailed test, which means we're saying our alternative hypothesis would be that mu1 is greater than mu2. The level of significance is a 0.5, and now we're ready to compute the test statistic. Now as we go to find T0, we already know mu1 minus mu2 is going to end up being 0, since one more time that's based on our null hypothesis, where those two are equal to each other. However, we don't have the sample mean for each of our samples yet, since we were given the raw data. Now this is where we can actually jump over to the calculator in order to help us gather our information, because we need x bar 1, x bar 2, and we also need the sample standard deviation from each of our samples. So jumping to the calculator portion in our notes, we're looking to use the two-sample t-test function in order to gather all our data. Now this function is going to give us our p-value, which we know we need for our conclusion. However, if it's a free response test, we can also gather all that needed information to show the math that's going on behind the scenes. Taking a look at the calculator then, like you see on the notes, first we're going to hit stat, and hopefully we're feeling comfortable with this now. We're going over to test, and you see option number 4 would be the two-sample t-test. Remember, it's a t-test because we're conducting a hypothesis test on means, and it's two-sample because we have two independent samples here. Hitting enter to input the details of the test. We have data highlighted already. If we were given x bar 1 and x bar 2, we'd head over to stats and hit enter, and then enter those details. But since we were given the raw data, remember we input that data into L1 and L2, so we're saying list number 1 is L1, list number 2 is L2, Our frequencies are 1 since we don't have grouped data. And then our alternative hypothesis is this statement where we're saying mu1 is greater than mu2. In case that ever gets confusing, this line simply matches the alternative hypothesis. We're going to say that our test is not pooled because we use that only when we know or assume, because sometimes we can be told to assume, that both sample standard deviations are equal. They didn't say anything about that, and most of the time they won't. So 99% of the time we'll be using a setup where it is not pooled. And finally, you have the option to calculate or draw. We'll hit calculate for the moment at least. And we end up with a whole bunch of information for our 2-sample t-test. One more time, notice that they already gave us the t-statistic, and we have the p-value like we previously stated. But right now we're working with a free response situation where we need to show the math on how to find our t-naught. So this is the information we're looking for. X bar 1, X bar 2, and notice we also have S sub 1 and S sub 2. That is, taking a look back at our notes now, we have the 2 sample means, and we have the values of our sample standard deviations, so we can go ahead and substitute those values to show that we know how our test statistic is computed. Well, substituting what we used the calculator to find then, we found X bar 1 to be approximately 5.702, and we found X bar 2 to be approximately 5.649, and we're going to subtract 0, as previously discussed, which would be the difference between mu1 and mu2. And then substituting the values we have for our sample standard deviations, we found S sub 1 to be a 0.0497. Remember, we need to square those though. And S sub 2 was a 0.0689. And our sample sizes being 18 and 16. Well, we can input all these details into our calculator. Or remember, our calculator also gave us the t-statistic. And remember, that was approximately 2.537. Well, now that we have our t-statistic, we can head over to step 4, where we need to find the p-value. Remember, to find the p-value, we need to use the tcdf function, and we also need to remember to draw the curve. And the one extra thing we need to remember is that we need to use the smaller of our sample sizes as our degrees of freedom. Well, drawing our generic t-distribution curve here, remember we're talking about the standardized version, so that means our mean value would be 0. We just found our t-statistic to be a 2.537, so we're about 2.5 standard deviations above the mean. And remember, we're working with a right-tailed test. So with that graph in mind, now to find the p-value, we simply need to find the area under the curve that we have shaded. That means to find the p-value, as previously stated, we're using the tcdf function. Our lower limit is that 2.537. We're going up to infinity, and our degrees of freedom would be 15, since that would be the value of our n sub 2 minus 1, meaning we had 16 pieces of data in our second sample. If we input that into our calculator, we get a p-value of approximately 0.0114, and we know to compare that to our alpha level of a 0.05, which means we have a p-value that is less than our alpha, and we know that means we get to reject our null hypothesis. That is, there is sufficient evidence to conclude that the mean weight of state quarters is greater than the mean weight of traditional quarters. And that means we're all set with our first example of testing hypotheses regarding 2 independent means. And that takes us into our next objective, where now we're discussing how to construct and interpret confidence intervals regarding the difference of 2 independent means. So we're still talking independent sampling here. And we have our formulas for the lower and upper bound. Like we've done previously, we're allowed to bring those together using just a plus or minus symbol, which we'll show in the example. Hopefully this is feeling a bit familiar, but of course one thing to emphasize, our critical value t sub alpha over 2 is computed using the smaller of our n sub 1 minus 1 or n sub 2 minus 1 degrees of freedom. That is, again, the degrees of freedom comes from the smaller of our sample sizes. Well, if that's okay, let's go ahead and jump into our example. We need to construct and interpret a 95% confidence interval now about the difference between the population mean weight of a state quarter versus the population mean weight of a traditional quarter. So we're just pulling on the previous example, and we have our data in L1 and L2 already. Remember, we verified that the requirements have been met already for the hypothesis test, which means we're also okay to construct a confidence interval. If we're okay with that, writing our formula one more time, but blending our lower and upper bound together, we have the formula for our bounds. From the previous example, we found a lot of this information. We found x bar 1 to be approximately 5.702, x bar 2 was approximately 5.649. We've got that plus or minus our t sub alpha over 2 being multiplied by our sample variances, where the first sample had a standard deviation of a 0.0497, but we need to square that value, and we're dividing that by the sample size of 18, adding that to our sample standard deviation for the second sample being a 0.0689, squaring that of course, as called for by our formula, and dividing that by the size of our second sample of 16. So the only thing left would be to find our critical t value of t sub alpha over 2. Well, first we need to find our alpha, which we know is the complement of our confidence interval, and we're told to construct a 95% confidence interval. So our alpha is our 1 minus our 0.95, giving us an alpha of a 0.05, and that means alpha over 2 would be a 0.025. Well, if that's okay, then we're trying to find t sub alpha over 2, which would be more specifically a t sub 0.025, and that means we need to use our inverse t function, with our 0.025 being the area to the right of our critical t value. So we're inputting inverse t, 1 minus our 0.025, and our degrees of freedom is again 15, which would be the smaller of our two sample sizes, minus 1. If we input that into our calculator, we end up with a t sub alpha over 2 of approximately 2.13, and we can substitute that into our formula for our lower and upper bounds, which means we have all the math to find our lower and upper bounds. And that means we can input all these details into our calculators, or like we did previously, we could jump over to the calculator portion to get our results. Well, heading over to the calculator page in the notes, we're constructing a 2-sample t interval now, and just emphasizing that one more time, it's 2-sample t interval as opposed to test, because we're constructing the interval, not conducting a hypothesis test. If that's okay, let's head over to the calculator. As we see in the notes, I'm going to hit stat, I'm going to arrow over to test, and option 0, if you want to arrow down to it, or just hit 0, will take you to the 2-sample t interval function. Hitting enter to take a look at the details, we still have our data from the quarter examples in our L1 and L2. Our confidence level needs to be a 0.95. Pooled is still no, as previously discussed, and will be most of the time. And we can go ahead and hit calculate in order to find our 2-sample t interval. One little thing of note here though, is our interval might be slightly different if we were to put in our by hand formula, and one of the main reasons would be take a look at the degrees of freedom. From the calculator, the degrees of freedom is calculated in a more complex way than simply taking the degrees of freedom from the smaller of the two sample sizes, but we don't go into that detail in our textbook, so that's why our by hand math might be slightly different than our calculated confidence interval. Either way you get your confidence interval on a free response question is acceptable. For the sake of our notes, I'm going to go ahead and use these results as our confidence interval. That is, we found our lower bound to be approximately 0.0101, and our upper bound looks like it's approximately 0.0956. Heading back to the notes then, just repeating one more time. From the calculator, we found our lower bound to be approximately 0.0101, and our upper bound to be approximately 0.0956. But one more time, that's probably going to be slightly different than if we input these details in our calculator altogether, but both results are perfectly fine if it's a free response question on the test, as that's likely just a result of the different calculations in our degrees of freedom. If we're okay using those results from our calculator, then we have our confidence interval, and wrapping that up with our interpretation, we are 95% confident that the difference between population mean weights of state quarters and traditional quarters is between 0.0101 and 0.0956. Now, just to add on to this conversation, we want to be able to connect confidence intervals now to a hypothesis test. That is, we've conducted the hypothesis test on this data already, and now we've constructed the confidence interval as well. So we want to tie those two ideas together. Well, since the confidence interval does not contain 0, we can conclude that the state quarters weigh more than their traditional quarters. That is, tying these two examples together one more time, remember we previously rejected the null hypothesis that state quarters weighed the same as traditional quarters, since we found a small p-value that was less than our alpha, and our conclusion was that there is sufficient evidence to conclude that the mean weight of state quarters is greater than the mean weight of traditional quarters. Well, keeping that conclusion in mind, and taking a look at our confidence interval, remember we're 95% confident that our confidence interval contains the true parameter. So we're 95% confident that the true difference in the mean weights between state and traditional quarters is between a 0.0101 and 0.0956. Well, if that's true, and the truth is in that confidence interval, the confidence interval does not contain 0. So we're 95% confident that the difference between these mean weights is not 0, and that's how we're able to conclude that state quarters weigh more than traditional quarters. That is, in general, if we're constructing confidence intervals about the means of two different populations, and those confidence intervals do not contain 0, then that is evidence to conclude that there is a difference between the two populations. Now the second layer is that we're able to say that state quarters weigh more than traditional quarters. And that's because our confidence interval contains only positive values. Remember, our comparison was from state to traditional. And since our confidence interval represents the mean difference between those two populations, if we have a positive result, it means that state quarters must weigh more than the traditional quarters. If these two values were negative, then that would tell us that the state quarters weigh less than our traditional quarters. It's a bit of a tough concept here as we're getting pretty deep trying to connect these confidence intervals to hypothesis tests, but hopefully you're feeling alright. We've worked with the calculators and done our by hand math, which means we're all set. And thank you for joining us one more time in our discussion of the inference about two means, now working with independent samples.